There should be descriptions and chapters with timestamps down in the description of the video, so you can just go ahead and click to whatever setting you're trying to figure out how to use. Otherwise, come and just hang out with me, and you might learn a thing or two about using your little multimeter. Hey folks, welcome back to the channel. And for those of you that are new, my name is Luke, and today we're going to be reviewing all of the different test settings on your AstroAI DM6000AR. I've had AstroAI on the show a bunch of times, and I think they're a perfect line for hobbyists and enthusiasts learning electrical. They've got a lot of bang for their buck, so why don't you grab a snack, have a seat, and let's dive into this AstroAI. We'll start off with your leads. Black lead lives in your COM port at all times. Make sure that it is fully seated. Your red lead is going to live in this main input port for like 99% of the time. Every once in a while, you're going to need one of these special settings, and so you're going to have to switch your leads over. When we get to those parts, we're going to, I'll make it very obvious that I'm switching the lead over, and we'll talk about why it's set up like that and why you need to be extra careful. But for most of the time, this red lead is just going to live in this little port here. So let's start with our first setting and kind of look at the lay of the land. I mean, we've got volts DC, volts AC. This is your resistance, continuity, and diode, capacitance, Hertz and duty cycle. This is thermocouple, that's in Celsius and Fahrenheit. HFE, that's what this adapter's for. It's for transistor testing. We'll talk about that. Then you're going to have micro, milli, and whole number amps. So these are all for measuring current, and it's rated for both AC and DC. Then low Z, we're going to talk about, that's a very special handy function, and then a secondary off position. Relative is going to be like a delta. Then your range, it's an auto ranging meter, but you can manually range it if you'd like to. It's a 6,000 count meter. Select, hold, min, max, backlight. Ooh, I do like this big display. I like it in black. I've done a video on this one and I had it in blue before. It looks a lot better in black. It tells us we're in the DC voltage setting right now. And then you can see down here, it's going to default to millivolts. So it's like the lowest setting that it can go to because there's no voltage hooked up to it. You'll want to pay attention to that. But if you'd like to manually change that, that's what your little range button here is for. You're going to see this decimal hopping around on the screen. And you can read whole volts to the 1,000th place. Yeah, something I'd like to see when you run through the range button, because you might accidentally hit it. If there was an auto button so that you could hit it to just go back to auto instead of having to flip and then go back, that would be nice, but that's neither here nor there. Okay, so we have your red lead. We have your leads, black and red. Black is for common. Think of black like negative, common, ground of your circuit, and then red is hot, right? That's why it's red. It's for the positive. Battery as an example for measuring volts DC. You can see we have plus and minus. So I would put my red to the plus and my black to the minus, and then I would get a voltage reading to the 1,000th place. Something that we want to think about whenever we're measuring DC is directional. It only goes and flows in one way, right? As opposed to AC alternates back and forth between plus and minus, where DC is just a straight shooter. If I used my black lead on the positive and my red lead on the negative, I'm going to get that negative symbol displayed here on my meter. And all that's saying is that the flow is in the opposite direction of what the meter is anticipating. So if you see that negative sign when you're doing DC measurements, that's what it's indicating. Something that people usually like to see is like, okay, but what about my car battery? Car battery is going to be the same concept. Red to positive, black to negative, and you'll see a voltage. Now, a little trick that you can do if you want to check your cold cranking amps on your car battery is while you have your meter hooked up to the positive and negative terminal leads, you can have someone turn the engine over, and then you can look for the voltage drop and then check it online. I'm sure you can find a chart somewhere. Let's do volts AC. We're going to use a little outlet as an example. Now, if you're just checking your normal standard home outlet, I'm sure you've seen them in the hardware store, just get a dedicated outlet tester. They make this process way easier and they're very inexpensive. And what we can see here is I have these two LEDs illuminated, and then I have a chart here and it's telling me, hey, my hot, my neutral are reversed, and it gives me a voltage all in one go. So it makes it super easy. But I understand that's not always the case, especially if you're going to be checking like a 240 outlet or maybe not a standard configured outlet such as this. And I'll show you how to go ahead and use your meter to determine like if a hot and neutral are reversed. We will want a ground for this testing. If not, go find a ground somewhere in the house and run a piece of wire from it to here, and then obviously be super careful because then you're having a direct path to ground available for the electricity, but you're going to need it for this type of testing. So I can go ahead and insert my test leads into my prongs and use them to open the doors, and we're getting a voltage. So we have voltage here, that's great, but there's no indication that the hot and the neutral are swapped. So how would we go about that? And that's where our ground pin comes into play. What we can do is just take one of our leads out, put it to ground. And so now we're seeing the slot on the right of our outlet and the ground. We have very little difference in potential. We're showing 142 millivolts, which is like nothing. Then I can swap my leads again. I've got this lead in the left-hand slot and I go to ground. Okay, and now I've got my 120 back. That's telling me that this one is the hot and that they're backwards because the hot is supposed to be on the right-hand side. Okay, resistance, continuity, and diode. Let's see, it's going to default to resistors. So let's talk about resistance a little bit. You don't need a continuity because you can hit the select button. That'll bring you to diode and then continuity. And then back again will bring us to resistance. Resistance measurements isn't just for testing resistors. I've got some here so we can look over the measurements. But resistance and continuity are kind of one and the same. And when we're looking for continuity in a circuit, we're looking for a low amount of resistance. Okay, so there's about 1.2 ohms of resistance in the circuit. There's some amount of resistance here, which tells me that there's some type of continuity, as opposed to if I did the same test and I just got this OL here, that stands for open loop, which means that my circuit would be open, right? But let's just run through some resistors and check our measurements. Something that we want to be paying attention to here is where our decimal is at and our units of measurement. So we see 0.982 K ohms. What does that mean? Well, that K represents 1,000. So we need to take this number and times it by 1,000, and that's our true measurement. So we really have 982 ohms of resistance. Let's try another one. Okay, this time it shows 326 or 327. There's no K or capital M, as in Mike, next to our ohms. So that's just telling us, okay, this is just 326 ohms. This time I have 1.045, but I have an M as in mega, or think of millions. I need to times this number by 1,000,000. The way that I think about it is I just think of this decimal as comma. To me, I just think of that, oh, this is just 1,044,000. 1000 ohms. Next we have diode testing. So I have a diode here. Diode should have a stripe on it. This one's kind of faint to see, but right now it's on the right-hand side of the diode. I'll put my red lead on the left of it and my black lead on the right. And what we're seeing right there is the amount of voltage drop across the diode. Okay, so there's a decimal there and a V. So it's telling us this is 575 millivolts of voltage drop, or 0.576 volts. And we want to see generally between 500 and 800 millivolts of voltage drop across our diode in one direction. And then in the other direction, we want to see that OL stay there. And that's telling us open loop, or that there's no backflow. This diode tests good. And then next up, we can do continuity. A lot of you ask me in the comment section all the time about continuity checking. And continuity is you're just looking for flow to check for opens. It's usually one of the first electrical tests that you'll do when you're troubleshooting. So we could take this motor here. It has 2 terminals, and I'm just looking for continuity, right? Makes a little tone, and it displays the amount of resistance in that load, letting us know, hey, there's continuity. You can do the same thing here with this little light bulb. Same kind of deal. Or what I use it for the most is when you're working with larger circuits, wires are usually buried behind walls or dashes or under, they're hidden, right? So we're normally never able to see both ends of the wire just in one spot. And so we can use continuity, we can put extensions on these leads, and then we can see, oh, okay, that red wire goes to that terminal, but this black wire does not. This black wire goes to that terminal, and they don't go to each other. Capacitance. We've got 2 examples here, one for the homeowner and one for the electronics hobbyist. Always want to make sure to discharge your capacitors before you test them. This is for your safety and so you don't damage the meter. For here we have, as a homeowner, you're probably trying to figure out how to test your AC run capacitor. Notice that the amount of capacitance for this is very small. So this is 35 microfarads and 5 microfarads. There are 2 capacitors in here. They share a common terminal. That's why it's labeled C for common. And it's real easy because we have common terminal on our meter labeled already. So we know, okay, put our black lead here, put our red lead to this other terminal. That'll tell us, okay, there's 35 microfarads of capacitance there. And then we can put it to the other terminal. And we've got our 5 microfarads of capacitance there. So the capacitance of this capacitor is testing good. Now we have, this one is rated for 680 microfarads. So you might be thinking like, okay, this one only says 35 microfarads and this one says 680, but this one's way bigger. The reason why this one is much bigger is so it can handle higher voltages. This one is rated to handle 440 volts AC. This one can only handle 16 volts. A capacitor size isn't necessarily the amount of capacitance, but the amount of voltage that it can handle. This one does have polarity, so it has a negative sign and then no sign here. So we'll put our negative sign to our common lead and then our red lead to the other. Give it a second to charge. And it comes back as 640 microfarads. Notice how it has an M for milli instead of that funky U like we would see. Milli is the next unit of measurement up. So 0.640 millifarads equals 640 microfarads. And then another thing you might be wondering is, okay, well, if it's 640 microfarads, but it says 680 on the capacitor, is that a bad capacitor? Capacitors will have a tolerance for their capacitance level. So like this one tells us up front, this one needs to be within plus or minus 6% of these values. I believe the packaging for this one says it should be plus or minus 10% of this value. So that's why the number may vary a little bit while you're testing your capacitors. All right, Hertz and duty cycle. I've got another cool little meter by AstroAI, the AM33D. And this actually outputs a square wave. When we're working with like controllers and pulse width modulation, like digital outputs and inputs, Hertz and duty cycle might be important information to have. This little meter outputs a little square wave. And if we were to look at it on an oscilloscope, it would probably look something like this. It's like 3 volts and that's like 0. Okay. And it's pulsating. We use pulse width modulation a lot in automation and a lot in automotive. I can't remember if this one is advertised as an automotive multimeter. There's a couple things that we might want to know about this square wave that this setting can help tell us. And that's going to be how long are pulses turned on for, and then how often are they turned on for. And so we have Hertz, which is how many times something turns on and off in 1 second. And then we have duty cycle, which is expressed in a percentage. And that's going to be how long these pulses are on. So right now, this one looks to be about 60%. It looks like 60% of the time it's on and then 40% of the time it's off. So we can use Hertz and duty cycle to measure a square wave output to get this information so that we can kind of draw a picture in our head of what's going on with our square wave. It's going to default, it goes to Hertz first, and you can see the square wave being output by this. Looks like it turns on and off just over 47 times in 1 second. And then we can go to select. That'll bring us to our duty cycle. And it looks like our square wave is about 50%. So it's on about 50% of the time and then off 50% of the time. Okay, we're going to swap out our leads. Notice how they've been in the same ports the whole time up until we got to thermocouple. We have our thermocouple leads. I'm not a big fan of these just because when you're pulling these in and out of your meter, it can be really easy. They're not fully inserted, just for example. It can be really easy because they can get stuck, and you'll pull out one at a time. And as it lets go, you'll pull it back, and it puts an incredible amount of tension on this one and on this one. So they fail really easily. That's why I'm not a big fan of this style. So thermocouple, really easy. Just going to do red to the input like we had before, black to common just like we had before. It's going to default to Celsius, so you should be able to hit select, and that'll bring us to Fahrenheit. And then something that I like to do is, I don't think it's that cold in here, but to double check that my thermocouple is working properly, I'll always put my fingers over the lead tips and make sure that it goes up to an appropriate temperature to make sure that I have good integrity in my leads. And then again, just be real careful pulling those thermocouple leads out. If you're not sure what the application of a thermocouple would be, really great for measuring super hot and cold things. Okay, HFE. I'm gonna say my piece for now and for always. Just hear me out. Transistor testing on meters is just not a good idea. They have purpose-built testers for transistors that are incredible. This one's even a little outdated, and it is way better than anything that you're going to find in a meter. It automatically labels the terminals and the type for you. It gives you a bunch of information. Getting a little multifunction tester like this, I should have one in my Amazon store, but you can just type in online transistor tester and they should be like 20 bucks or something like that. The next 3 settings here, this is going to be for microamps, milliamps, and amps, and they're rated for AC and DC. The squiggly line indicates that it's rated for AC, and then the solid line indicates that it's rated for DC. This portion is going to be manual ranging as opposed to like your resistor and your voltage measurements where it's auto ranging and it can read a huge variety of numbers for you. To make the amperage readings accurate, you have to manually select it. And the way that I would really recommend going about this is if you're going to measure the current of something, One, we have to do it in series. Two, we have to make sure we're in the right port. And three, I would always start at the biggest setting. I would start at the biggest setting. I would take a measurement and see how big or small my measurement is, and then adjust accordingly. Okay, so we're going to do some examples of that. Black lead into COM, red lead into the 10A, stands for 10 amps. These are fused ports. I'm also on DC. If you're trying to measure AC currents and you're getting funky numbers, make sure to double check that it's on AC. So you should be able to select and go to AC, because it'll show numbers on either setting, but if you're on the wrong setting, your numbers are going to be wrong. These examples are going to be in DC. Okay, something to think about. When we've moved our meter lead over to a different port, we've changed the configuration of how the leads are going to respond to voltage and current. And that's something that we need to take in consideration. When our leads are configured like this, we have essentially turned the ends of our meter leads into one continuous wire. If I had some kind of electrical component like a capacitor or a battery, or some kind of circuit, and I just put one wire to one and one wire to the other end, well, I would have created a short circuit. So it can be really easy to create short circuits when we're in this configuration. So we want to be extra super careful about how we measure things. And what that means is, like, an example would be, there's voltage present here. If I went to measure, even if I changed the setting here and I went to volts DC, and this is DC voltage, and I went to measure this, I would create a short circuit and I would pop the fuse in my meter. And then there's a chance I could damage whatever I'm trying to measure. That would be known as a parallel measurement. What we need to do is make a measurement in series. What do I mean by that? I have voltage present here and I have a load, but I have an incomplete circuit. We can see that there's continuity through the ground side of my circuit, but there's not through the positive side of my circuit. And since now my meter lead ends, there's no difference between them and a jumper wire, I can take advantage of that. And instead of using a jumper wire to just complete the circuit like this, I can now use my meter leads to complete the circuit and make a measurement at the same time. So notice I completed my circuit, my load has turned on, and now I can measure current. And I'm coming back with 2 amps of current. We want to think about the other current settings that we have here. 2 amps of current is much, much larger than milliamps or microamps. So we're in the best setting to get the most accurate measurement. And we can even read our measurement down to the thousands, which is really cool. We're going to do a few more examples. Very similar scenario. We have a load. We have voltage present here. We have an incomplete circuit, but this time the ground side of our circuit is missing. Can I still measure the current? Well, yeah, I still can, because current, when we're having electrical load, for it to work, current has to flow through the whole circuit. So there's going to be current on the positive, there's going to be current on the negative, but we need a complete circuit for current to flow at all. So even though we have voltage present, no current is flowing through our circuit. And I can go ahead and measure it. My load is turned on. I've completed my circuit with my meter leads, and I'm taking a measurement. There's a couple things to think about. One of them is, notice that I changed the direction in which I was using my leads. I can still measure it in this direction, but this time I get a negative sign. So kind of like what we talked about earlier with DC when we were measuring a battery with the plus and the minus, and we put the black lead on the positive and the red lead on the negative, and we had a negative sign. It's the same thing here. The current is just moving in the opposite direction of what the meter is anticipating. And on old meters, old analog ones, it would have just pegged to 0. This time with our digital ones, we can see and still measure the current it just displays a negative sign to let us know, hey, it's going in the other direction. And if that's confusing or throwing me off, I can change my meter leads around so that my flow is going this way, and now I no longer have that negative sign, okay? Let's talk about the amount of current that we're measuring. Are we ready to move down yet? Well, this is where we're gonna want to pay attention to the limitations of the next port down. So I'm supposed to use this one for HFE for my transistor testing, or I can use it for microamps, or I can use it for milliamps. This one is rated for 10 amps, and this one's rated for a maximum of 600 milliamps. This load is 429 milliamps, and that is less than this 600 milliamp. So in theory, I should be able to swap over to here and move down to the milliamp setting. It would convert my units of measurement into milliamps, and then I would see 429 as a whole number. So let's go ahead and try that. Great. And so now we can see it's a much more accurate number. I can read it to the tenths, and we're in that milliamps. Let's keep going. Okay, so this time it's the exact same setup. I'll be making my measurements in series, just wired a little bit funky. And then I'm using resistors because they make excellent small controlled loads. And you can use the amount of resistance that you have with Ohm's law to calculate what amperage you should be expecting to read on your meter. But I like to use it for nice and small controlled loads. We are in the milliamp. And let's see what measurements we can get. Again, I'm still have a DC power source, so I'm still in the DC setting. If you're trying to measure AC current, please double check and make sure that you're in the AC setting, because it will default to DC every time. And then if you're trying to measure AC current, you'll get the wrong number and it'll be really confusing. Okay, so we're at 37. Let's keep bringing it down. 12. Now we're getting small. 1.19 milliamps of current. And another way that we can think about this is 1,190 microamps of current. So we're getting ready to enter into the microamp territory. And I think that we can just go ahead and move that down, and we can. And now we're back to whole numbers, 1,190 microamps. And then I should have one more down. There you go, and 121.4 microamps of current. Very, very small amount, very precise, very cool. So we've got a little bit of a game to play here, and this is going to be really handy if you work with a lot of AC circuits. And AC circuits are really cool. They've got a lot of really cool principles to them, but some of the things that make them really cool can also cause us troubleshooting nightmares. And so we're going to start out with a scenario that you're working, you're troubleshooting power supply to something in a box somewhere in an industrial environment. You have a hot and you have a neutral and you have a ground. And we're just going to go to the normal volts AC setting. So let's just go ahead and measure this out. So I'm going to measure from my hot to my neutral, and I have 20 volts AC. From my hot to my ground, I have 146 volts AC, and from my ground to my neutral, I have 27 volts AC. That could be really, really confusing, and if you saw that out in the field, you would be like, what in the heck is going on here? This is where the low Z setting comes into play. I'm going to make sure that it's on AC. The thing about the low Z setting is whenever you try to read about it or look it up, at least what I experienced is it made me think that I had to know the impedance of the circuit that I was working on, and you're not going to know that off the top of your head. What they're talking about is the impedance of the meter. When you're in a low Z, Z stands for impedance, we're lowering the internal impedance of the meter. And what this is going to do, think about Ohm's law, as we lower the impedance value, we're going to raise the amount of current. So by lowering the impedance value of the meter, we're going to put a very small load on our circuit, and it's going to drop off any ghost inductive voltage. Notice how these are coiled up. Also notice how my neutral is not attached to anything. I shouldn't be having any voltage on there. Now that we're in the low impedance setting, let's take our measurements again and see what we get. From my hot to my neutral, 500 millivolts, that's nothing. That's just noise floating around the world, right? From my hot to my ground, okay, 145 volts. That's telling me on my hot, I actually have 145 volts of AC. But from my neutral to my ground, 900 millivolts. Remember, it was like 20 something volts that was up there. Let's move it back to volts AC. Yeah, I was showing 30 volts AC between my neutral and my ground. So why would there be 30 volts there? I go to my low Z setting. I make sure it's on AC. It drops off almost all of that ghost voltage. Because as you can see, our neutral is not hooked up to anything. And our ground is actually grounded. So there shouldn't be anything there, right? And that's reflected in the low Z setting. So I hope that makes sense. I hope that helps. If you got any questions, let me know down in the comment section. I'd love some feedback. And if you're all learning this stuff, I have a bunch of different shorts explaining in bite-sized pieces different electrical concepts that you can use to help you with troubleshooting, or if you're trying to learn a concept for a project or for work or for whatever. So be sure to go check them out. I also have a ton of other meter videos. If you're browsing for different meters and you want to see the features and how they all work and what they're for, go check them out, and I'll catch you on the next one.